Hi, everybody. My name is Vasily from PyTorch.
And I'm Driss Guessous, also on PyTorch.
And today we'll talk to you about microscaling formats in PyTorch, mxfp8, mxfp4, and nvfp4. And we'll just switch off kind of speaking during the talk. So outline what we'll cover today. We'll cover what these formats are. We'll cover some of the building blocks in PyTorch that you can use to build things with these formats. And we'll cover some performance kind of tips for training and inference with these formats. So first, I just have 2 slides explaining what are these new formats and why you might want to use them. And the first slide is very high level. On the left, you see a bfloat16 kind of gem. You have a tensor. You want to put it through a gem. Why you might use these formats. If you quantize your tensors to mxfp8, you pay some overhead to cast it, and you might lose some precision. But then you get a tensor at 2x smaller, and your gem can run up to 2x faster. And then all the way on the right, if you use 4-bit formats, such as nvfp4 and mxfp4, your tensor is even smaller, and your gem is even faster. So basically, it's a performance versus accuracy trade-off. And this is a very dense table. I apologize. But this table kind of talks through what these formats are specifically and how they're defined. So first, mxfp8, you get a compression ratio of almost 2x. Your gems can be faster up to 2x. You're not going to see exactly a 2x, but it's a theoretical upper bound. It's supported on the new NVIDIA and AMD hardware. The element dtype is float8. The scale dtype is float8 E8M0. And we're going to talk about what that means further out on the slide. And it's a quantized format with a block size of 1/32. Then in the middle, we have mxfp4. It's basically mxfp8, but fp4 instead of fp8. So compression is almost 4x. Gem speed up is up to almost 4x. Same hardware. The element dtype is also new. It's float4, and we'll talk about specifically how that's defined. And the block size is the same as mxfp8. And finally, all the way on the right, nvfp4 is another 4-bit format we have on PyTorch now. And this one is only supported on NVIDIA hardware. The element dtype is float4. The scale dtype is float8. And the block size is smaller than the MX formats. The block size is 16 unpacked or 8 packed. And there's also an outer scale, which is a float32. OK, so in the next section, we're going to cover some building blocks in PyTorch that you can use to use these formats. And before I dive in, the slide represents like a high-level overview of how these building blocks fit into quantizing a tensor and then doing a gem. So the second box, it represents the scaling. So if you want to scale your tensor to mxfp8, you need to use the new scaling format, which Driss is going to talk about a bit further. Then the third box is you need some new dtypes to represent the data in the scale of an mxfp8 tensor. And we'll talk about the dtypes. And finally, you can call new low-precision gems in PyTorch to get the performance benefit when you do your gems. And Driss is going to talk about those. So first, let me cover the 2 new dtypes in detail. And the first new dtype we have is called float8 E8M0 FNU. It's a very fun name to pronounce. And what this dtype means is this is an unsigned exponent of a float32 or a bfloat16. So on the top of the slide, you have your bit representation of a float32 number. If you just take the exponent bits, either take them as is or you do some rounding, then you'll end up with a float8 E8M0 FNU. And the quick explanation of what does the FNU mean? F means this is finite encoding. N means there is a NAND, but it's a non-standard NAND. It differs from the IEEE 754 spec. And U means there's no sign bit. So this is an unsigned encoding. And what is this dtype used for? This is the scale dtype for the microscaling formats mxfp8 and mxfp4. You can do power of 2 scaling with this dtype. It's available on PyTorch 2.7 and higher. And I also call out this is the shell dtype. So you cannot just call any op on it that supports only a very limited number of ops. So what you can do is you can create tensors with the dtype. You can move bytes around, so you can concatenate things, you can view, you can reshape. You can cast from high precision to the dtype, and you can use this as a scale input to the new gems that we have on PyTorch. And the second dtype I want to cover is called float4 E2M1FN X2, another very fun name. And this is basically two float4 numbers packed into a byte. So imagine starting with two high precision numbers, for example, float16. You have some routine to compress them to float4, and then you pack two of them together, and then you get this new dtype. Explanation on the suffix, F is finite, so there's no infinity here. N means downstairs nan. There's actually no nan in this encoding. And X2 means this is two numbers packed into one byte. And this is important because this is the element dtype for two of the 4-bit formats we now have, mxfp4 and nvfp4. This is available in PyTorch 2.8. It's also shell dtype. This one is even more shell than the previous one. You can basically create these tensors, and you can use them as scales for 4-bit jumps. Okay, so now over to Driss to talk about scaling.
Thank you. Okay, I'm going to give an overview of how to actually use these new floating point formats on the latest hardware with PyTorch. So if you were to store a high precision FP32 tensor, let's say directly in FP4, you would just simply lose too much information. You had 4 billion real numbers, and like we've seen, you only have 16 for these new dtypes. So one critical technique for preserving accuracy when we're going to these new formats is something called scaling. The idea is pretty straightforward. At a high level, we're storing a high precision tensor as a low precision tensor plus some scales. And those scales are typically also tensors. And we do this, right, to minimize the loss of information. Before this talk, you might be saying, I know how to do this. I can just call tensor.to float8. And the goal of this graphic is to try and convince you not to do this. On the top, we have a normal distribution. It's pretty wide, but it's not uncommon to see tensors with extremal values in this range, in this magnitude. And in this case, the extremes are at 800. So if we were to directly cast to FP8, we would need to clip the maximum. We would need to clip these values to the maximum representable value. That's a tongue twister in FP8, which is 448. So everything above this limit will be clipped to 448. And on the right-hand side, we can see some metrics for how much information we're losing in this process. The MAE is the mean absolute error across all the values in the tensor. And when we compare it to the original, this quantized and dequantized version, we can see pretty high error magnitudes, up to 352. And the bottom is using a very basic scaling recipe called per tensor scaling. And by the numbers, we can see this basic recipe already greatly improves the MAE and the max error. Okay, so these are some of the basic formulas for how we calculate scales. The numerator is, again, the maximum representable value in the dtype that you're going to be casting to. And the denominator is the runtime calculated Amax in the tensor that will be casted. So in the case of FP8, we have 448. And for FP4, this would be 6. And you might be wondering about the extra powers of 2. Again, this is related to the E8M0 dtype. And this is the base intuition. If the scale is greater than 1, we're going to stretch the values to fit within the range. And if it's less than, we're going to compress them. Okay, with this knowledge, let's look at two popular scaling recipes that have been used on Hopper and MI300 GPUs. On the left, we have per tensor scaling, and on the right, we have per row scaling. Some diagrammatic conventions first. These little windows and dash windows are tiles. They represent the granularity, which we're going to be calculating scales over. So for per tensor scaling, which is the simplest to understand, we have one scale factor for the entire tensor. And this window is, in this case, an m by k window. And for per row scaling, kind of as the name suggests, instead of using one window per tensor, we're going to use one window per row. And this gives us m different windows and m different scale factors. And this ultimately gives us more total scales. And empirically, this reduces the impact of outliers, and this leads to lower reconstruction loss. And notice in both cases, the scales themselves are stored in FP32. Okay, another very popular recipe. This was introduced in DeepSeek v3. And for their scheme, they actually use 2 different recipes depending on if the tensor is the activation or the weight of a linear or the MOE layers. The reasons for the different recipes per tensor type has to do with the need to transpose the weight during backwards. And if your block size is square, this ends up being faster to recompute. And so for the activation on the left, we use a window of 1 by 128. Or in other words, we break up the tensors into rows, and then we break up the columns into tiles of size 128. And this scheme is getting us closer to the new micro-scaled formats and the schemes they use. But again, in this case, the scales are in FP32. Okay, we should be ready to look at MX. So what's new? It's a little bit of a rehash of what Vasily said, but we're going to adopt the new blockwise scaling recipe, like in DeepSeek. And instead of using a 1 by 128 tile, we're going to use a 1 by 32. And instead of scoring the scales in FP32, we're going to use the new E8 M0 dtype that's been introduced in PyTorch. The let's skip that. And this is there's one other very important recipe on Blackwell, and that's the nvfp4, which Vasily discussed. Instead of a window size of 1 by 32, we're going to have 1 by 16. And although it may have seen that windows of scaling need to be non-overlapping, nvfp4 actually does 2 levels of scaling. There's one global scale per tensor, and that's an FP32. And then the 1 by 16 block scales, which are not stored in E8 M0, but are actually stored in FP8, specifically the E4 M3 variant. Okay, I threw the kitchen sink of recipes at you. I'm more of a visual learner, so I made some animations that took a very long time to create, so I hope you like them. We have the high precision tensor in bfloat 16. Let's first take a look at per tensor scaling. We're going to get 1 Amax tensor for the entire tensor. For per row, again, we're going to split the rows up individually, and then in these windows, we're going to calculate the Amax values. I couldn't fit 1 by 32 on the slides, so I chose a block size of 1 by 2. But again, you iterate along the rows and along the columns, calculating scales, calculating Amaxes. And once we have our Amaxes, we're going to plug this into that calculation, that formula I presented earlier, and this is going to turn these Amaxes into scales. Let's look back at per tensor, what the full flow is. We then broadcast this scale to every element. We do the pointwise multiplication, and we can directly cast to our new dtypes that have been added in PyTorch. Again, for per row, very similar. The broadcasting is only within a window. In this case, it's a row, and we cast. And finally, we have block scales. Again, each block scale only applies to the respective data. Okay, so what about performance? This is where kernel fusion becomes absolutely critical for the end-to-end recipes. These numbers are gathered on a B200 GPU, and we can see that per row and MX scaling can be done in a single kernel, while per tensor needs multiple kernels. And unfused scaling operations are slow. Why? Because without fusion, they require multiple round-trip memories, multiple round trips to and from global memory, and arithmetic intensity for these kernels or make them strictly memory bound. And so this ends up being very wasteful. And again, one of the primary benefits of these low precision MX formats is the dramatically increased compute throughput on this newer generation of hardware. And specifically, right, these formats matter most for matrix multiplication because that's where all the flops is. We want to make our GPUs go bare. We've done this work. We quantized down to low precision formats. We've explored different recipes for minimizing error. And now we have the ability to do this calculation in a single pass. But to actually realize the benefits, we need specialized matrix multiplication operations that can consume these formats. And this is where PyTorch's new public scaled MM API comes in. It lets you express the quantization recipe for your scales, your data formats, the layouts of those scales, and we automatically match it to high-performance gem kernels for the specific hardware you're on. You describe what you want, PyTorch handles the routing, and you get the right kernel. And while it's not shown in the slide, we also have a new public low-precision gem kernel, gem API, and this is very important for the new mixture of expert models that are very popular. Okay, so I said throughput is faster for these new dtypes, but how much faster? This is my classic caveat that benchmarking is hard and there's a lot of foot guns. This was done on a recent version of PyTorch on a B200 GPU. The gray bar plots are bfloat 16 performance. The purple is mxfp8 and the orange is nvfp4. The clear trend we want to see is arising for larger, more compute-bound kernels. we see the total flops and the speed up over bfloat16 approaches their theoretical values of 2x for mxfp8 and 4x for nvfp4. Okay, cool. So let's go over some performance considerations for training and inference.
Okay, so we'll just share some things which are important when you're doing low precision training and you think about performance. I only have a few minutes, so I'll only pick two. I can talk about this for hours. We'll talk about why fusing kernels is important and how much performance I can buy you. And we'll talk about kind of what size of gem shapes you should have to expect a speed up when you're training with low precision. So first I have a table here to demonstrate that you need to have fused kernels if you're trying to scale things to mxfp8. And this table has two rows. The first row is an unfused kernel to cast your bfloat16 tensor to mxfp8 across DIM0, implemented with native PyTorch ops. And the second row represents the performance of that same operation, but fused. We choose to use torch compile. However, one could write like a Triton or a CUDA or a HIP kernel to do the same thing. And for these implementations, the fused one is 34 times faster. So it's not a 2x, it's not a 4x, it's like 10x or more. So you really need to fuse your kernels. And also, if you think about your naive kind of low precision training recipe, you have your forward and backward formulas for going through major to multiply. And common gem kernels currently require the first operand to be in row major and the second operand to be in column major memory layout. And because of this requirement, you actually need to, for formats where your scaling is 1D, you need to scale each tensor 2 times to kind of get all these 6 low precision tensors. So in the picture format, you can see there's 6 2mxfp8 kernels here. So you really need to fuse your kernels, either with a compiler such as torch compile or by handwriting kind of the fused kernels relevant to your model to get a speed up over bfloat16. And the second thing I want to talk about is why you need to have large gems to see a benefit from low precision training. So I'm going to use mxfp8 in this example, but mxfp4 and nvfp4 are very similar. So I have a very simplified formula here on the second line of my slide. Basically, if you're trying to do low precision training, your baseline is your bfloat16 gem time because you don't need to scale anything for bfloat16. You'll see a speed up if the right-hand side of this formula is kind of smaller than the left. So on the gem, you might get, I don't know, 1.7, 1.8x, a little bit less than 2x. And then you pay some overhead to cast your tensors from high precision to low precision. At large shapes, your gem times are cubic, and then your scaling kernels are memory bound, so it's quadratic. And kind of the larger your shapes are, the more the cubic terms dominate, and that's where you see the speedups. So if you plug all of this into kind of a simple roofline model, and you plug in the memory bandwidth of your hardware and kind of the reported compute of the top computer hardware, in this slide we're using the ones from the NVIDIA B200 GPU. You can see that as your size of your gem increases, eventually you'll see the point where the benefit from quantizing the gem is larger than like the overhead you pay for scaling your tensors. So the larger your shapes, kind of the more you can get from low precision training.
Okay, some performance considerations for inference. Since weights are static for inference, we're going to quantize them once, and we typically store them in the checkpoints. And similar to training, the dynamic scaling for activations should also be fused into kernels. And this can be done, again, with either custom CUDA, Triton kernels, or torch compile. We've seen that how calculating at global scale can be very expensive compared to local scales. So for nvfp4 or other recipes that require per tensor scaling, this can typically be beneficial to be calibrated offline on some data that's representative of what you'll see during inference. And again, for gem shapes, they need to be significantly large in order to see the performance benefits. And this is, again, a simple roofline model, except now we don't have to do the casts for the weights. Okay. Any questions?
As far as I know, they don't have like these special precisions. So how do you leverage the tensor cores? Do those custom kernels like you have them before conversion, or do you not use tensor cores when using this?
Yeah, I think the question was as far as you know, the tensor cores don't have support for these formats. So how do we utilize them? So on B200 and newer, the tensor cores do have support. There's a block scaling recipes, block scaling PTX instructions specifically for these formats. So they have specifics for mxfp4, mxfp8, and nvfp4. The accumulator is always an fp32, but you can utilize the tensor cores for these instructions and these dtypes.
Libraries like Transformer Engine are doing very similar things. How do you guys compare to other open source libraries out there? And where do you guys see yourself differing? Thanks.
Got it. Yeah, so for this talk, we wanted to talk more about like the low-level building blocks of how PyTorch can give dtypes and gems to help other frameworks and other people build frameworks. We do have Torch.io, which I guess I'll go to. Oops, can you go back to presentation mode? So we do have a Torch.io GitHub repository, which has workflows for pre-training, QT, PTQ, and inference. However, what Torch.io is trying to do is trying to provide like a native PyTorch experience, which is very composable with all the other PyTorch ecosystem libraries, and it works on different types of hardware. And different frameworks out there might optimize for different things.
One question. We have a custom code compile and for hardware. It supports all of this new type and export native. Do we have a integration for the compile? All of your entities do you just plug in like the model by your size to Torch compile is out of it?
I'm so sorry. Could you repeat the question? I heard maybe 80% of that. I'm so sorry.
So I think that we have a Torch compile backend, which called OpenWinner backend, and it supports the compression with such types where you describe like mxfp4, mxfp8 natively. Would it be working from out of the box if we just take a model, like compress it for like CUDA backend or NVIDIA backend, and just compile it with OpenWinner? Or what should we do to enable that? Thank you.
And sorry, to clarify, you said your backend already supports all these dtypes?
Yes.
Then it should work. So I'd say for mxfp8, it really should work out of the box. For mxfp4, we're still working on making Torch compile fast. Oh, yes. If you go to the conference website and you go to the page for this talk, there is a PDF file with all these slides.
Thank you. That is the hardest part to post, but I can figure out a way to get them. Yeah, that's a great idea. I think we have time for one more. I think your question was the speed up for different block scales. When you say different block scales, the actual size of the scale? Yeah. For the new mxfp formats, the actual the minimum window size is defined by the hardware. So it is like constrained to 32. You can go bigger by like broadcasting the scale along a bigger tile. Not necessarily, yeah. I think it depends on your kernel and if you're able to still do it in one pass. I think that's the main point. Okay, cool. We're getting flagged off. Thank you, everybody.